Good morning, class, and welcome to another lecture in our continuing discussion on sustainable energy technologies. In the previous class, we started our discussion on energy storage, and we looked at some of the applications that an energy storage technology might have in terms of our sustainable energy transformation. Specifically, we saw that energy storage can be used as a utility level storage for renewable energy generation systems in order to cater to the intermittency and variability of renewable energy generation. It can also be used as short-term and rapid response storage systems to improve the quality of power that is being delivered to the grid from the renewable energy systems in order to compensate for changes in voltage and amperage due to unforeseen changes in the energy supply. For example, changes in the solar insolation due to temporary cloudiness, changes in the wind energy generation due to changes in wind velocity, etc. Another important place where energy storage can be used is off-grid distributed energy storage systems in remote locations where we have standalone renewable energy generation systems like a standalone solar farm or a standalone wind farm, and the energy storage is associated with that in order to deliver reliable power 24/7 to such a remote village or a location. Another place where energy storage is extremely useful now is integration into automobiles which are being run by electric batteries like EVs and hybrid vehicle systems. Here we have an entirely different set of engineering challenges. The energy storage system has to deliver sufficient power to run a car for several hundreds of kilometers for a single charge. It has to be recharged relatively quickly. It has to adjust to changes in speed, acceleration, deceleration. It has to be sufficiently mobile and lightweight to be installed in a car system, and it has to have efficient heat management techniques so that it does not overheat during the operational processes. Then we have non-energy grid related applications like electronics industry, like batteries for laptops, cell phones, etc. And we have discussed how the initial technological breakthroughs that made it possible to have lightweight, high charge density batteries for laptops, cell phones, etc. was the catalyst that was made it possible to deploy energy storage for renewable energy grid systems as well. So today, in our continuation of some of the characteristics of energy storage systems, we will discuss some of the parameters by which we judge the quality of our energy storage technology. So, our discussion today is on important parameters for energy storage technology. So first is round trip efficiency. So this efficiency or round trip efficiency of an energy storage system can be defined as efficiency eta equals to energy output from the system to energy input to the system. So here basically what we are saying is what fraction of the energy that is stored in the storage device is recovered for usage. Okay, so what fraction of the energy that is being stored in the storage device can be recovered for usage? Okay, so suppose you have an energy storage system that can absorb say 100 joules of energy and can deliver 95 joules. That is, during the storage process and the transmission process to and from the system it is absorbing and delivering energy to, 5 joules of energy is being lost. Then the efficiency of that system is 0.95 or 95%. Okay. So this is a very good measure of the efficiency of the storage system, because greater the efficiency, better is the energy that you are recovering from the storage device. As we will see, in many systems the efficiencies do approach 90-95%, whereas in other systems it can be as low as 20% or 30%. So clearly those 20% or 30% efficiencies are not very ideal, because that means for every 100 joules of energy you are giving to the storage system, you can only recover 20 or 30 joules, and the rest 80 or 70 joules is being lost during the storage and transmission. A second important parameter is specific energy. Specific energy. So this is energy stored per unit mass of the storage device. So basically it is the amount of energy that 1 kg or 1 gram of the storage device can store. Okay. Because it's a storage device, it cannot store unlimited quantities of energy. There is a maximum limit up to which it can store energy, and that limit per mass basis is the specific energy. So for example, suppose a 1 kg battery can store 10 kilojoules of energy, then its specific energy is 10 kilojoules per kg. Okay, so if you now install a 10 kg battery in a car, you will know that at maximum it can store 10 into 10, that is 100 kilojoules of energy at a given charge. Okay. So this is important for automotive and electronic storage systems, where lighter weight is an important criteria for design efficacy. And this is not to be wondered at. You want a lightweight laptop or a lightweight cell phone that is both light and can hold a lot of charge per charging. Okay, it can run for a cell phone. You see that it can run for say 12-15 hours of non-stop video. Those kinds of ratings are there. Its weight is 2 kgs, 3 kgs, etc. Right. Similarly, a car will use a lot of power. If you have a too heavy battery pack, that battery pack has to be carried by the car. Okay, so you lose a lot of power if the battery pack is too heavy. Okay, so it's a very important design criteria, especially where mobility is an important concern. Its units are joules per kg. Okay. Another related parameter for energy storage systems is energy density. So this is the amount of energy stored per unit volume of the system. So its unit is joules per meter cube. Okay. So this is important, where space constraint is a factor. Again, you have automotive applications, electronic systems, household, energy storage needs. So again, where portability is a constraint, you do not want firstly the system to be very heavy, and you do not want the system to be very bulky, that is it is a large volume. You want a smaller laptop, a smaller handy cell phone, or a compact car. In such cases, to fit the battery within the geometric constraints, you need a battery that has good energy storage systems. It can be a battery, it can be other things as well, as we will see. Good volumetric efficiency or volumetric energy density. That is, it can store a significant amount of energy per meter cube of space it is taking up. Okay, so that is what energy density is giving us. Okay. So ideally, for these kinds of applications, automotive, electronic, and household applications, you need an energy storage system which has both high specific energy and high energy density. That's the ideal situation. Then a very important parameter is depth of discharge. So this is defined as the fraction or percentage of total energy stored that has gone out, or in other words, discharged from the system. Okay, so depth of discharge is an important evaluating parameter. We will see how. Basic definition is, it is the fraction or percentage of the total energy stored that has gone out from the system at a given time. So suppose, again, all of you will be familiar with cell phone batteries. Once you charge it fully, it is showing 100% charge. After a certain usage, it is showing it's 40% charge. So 60% has gone out. So the depth of discharge is 0.6 or 60%. So that's the basic idea. So then, associated with the depth of discharge, we have an important performance parameter called the self-discharge time. Self-discharge time. It is defined as the time it takes for an energy storage device that has been fully charged to discharge down to a predefined depth of discharge value when it is in an idle state. So let's understand this. It is defined as the time, so it's a time. So units will be seconds, minutes, hours, days, years. Okay, it's time it takes for an energy storage device that has been fully charged. So you know it takes up a certain volume, it has a certain energy density or certain specific energy. So you know when it's fully charged, this many energy units have been stored in that system, has been fully charged to discharge down to a predefined depth of discharge value. This predefined depth of discharge value can be 80%, 90%, 70%, whatever. You should define it in an appropriate fashion when it is in an idle state. That is when it is lying idle. That is, it is not transmitting any energy to any system or getting energy out of a grid or a system. Okay, so it is just lying disconnected and idle, not acting, not consuming energy for any action, not giving energy to any system, not taking energy from any system, just lying idle, and the time it takes to get discharged to the predefined depth of discharge value, 80%, 90%, when it is at its idle state continuously. Okay. So self-discharge time provides an estimate of how long energy can be usefully stored for a certain energy storage media before it dissipates away. So think of a cell phone or a laptop, because it's the easiest example, all of you will be familiar. Turn it off, shut it down or turn it off at 100% charge. Keep it turned off for 3-4 days. Then turn it back on. You will see that the charge amount has dropped. Okay, for older cell phones and laptops, it could have dropped significantly. For newer ones, it won't. Okay. But suppose you define the depth of discharge as around 60%. That is the time it takes for the energy storage system in its idle state to discharge 60% of its energy while lying in its idle state. So in this specific example of a turned off phone, this self-discharge time will be the time at which the turned off phone, when turning back on, shows that it has 40% of its initial battery charge left. And it kind of gives an estimate of the rate at which that energy storage device is losing energy to the environment through various loss processes. Okay. So an ideal energy storage device should keep its energy for the entire time. So it will not have a self-discharge time at all. But this is not true for most systems. It will dissipate the energy it has stored slowly over time. And this basically gives you an estimate of how long you can store the energy in this medium usefully before it dissipates away to such a degree that it is no longer a useful storage medium. For some energy storage devices, that self-discharge time can be measured in hours or minutes or days. For other energy storage devices, it can be a week, a month, or an year. It can even be decades for certain types of systems. So for example, a battery has relatively short self-discharge time. Even modern modern lithium-ion batteries in cell phones, if you turn off your cell phone today and turn it on back in 7 or 10 days later, it would have lost at least 50-60% of its energy. So its self-discharge time should be counted in weeks. Okay. There are other systems whose self-discharge time will be in years. Okay, so those we will come across as we discuss these systems in more detail later. But it is a useful measure of the period for which this storage system is useful and applicable. Okay. So suppose you have an application where you want to store energy and want to reuse it within a period of days. So for such systems, energy storage systems with self-discharge time of a period of a week or a month is fine, because it won't lose a significant amount of energy in a period of day when its self-discharge time is for over 30-40 days. However, if you want to store energy for 6 months, okay, and use it 6 months later. So for example, you are thinking of a storage system for a hydroelectric power plant which generates most of its electricity in the rainy season, whereas summer and winter it doesn't generate that much electricity. So you want to store the excess electricity it generates during the rainy season and use it in the summer or winter season. Then you need an energy storage system whose self-discharge time is over an year or more, so that you do not lose a lot of energy over the 6 months period for which you want to store that system. And batteries are not such devices, right? So that is the kind of decision that a self-discharge time of a technology gives you. The last but very important performance parameter is cycle life. Okay. So this is how many times the energy storage system can be charged and discharged to a predefined depth of discharge value before its storage capacity round trip efficiency self discharge time, etc. deteriorates by a certain predefined amount. So this is another aspect of energy storage devices. If you use it over a long period of time, and here using means storing energy, then taking energy out of it, then again storing energy and then taking energy out of it, over time its performance characteristics degrade. You will see that its round trip efficiency will slowly go down, that is, it will lose more and more of its energy while during the storage and retransmission. Okay. So how much energy you are getting out of the system versus how much energy you are putting into the system. Its self-discharge time will decrease, that is, the time it takes for it to discharge to a predefined depth of discharge will grow shorter as it loses more and more of the energy to the environment through leakages and other things. Its energy storage capacity in terms of specific energy and energy density will also decrease. So it will be able to store less energy per unit mass of its system. Okay. And all of this happens because of aging. Its material properties, its performance properties starts to degrade through repeated use. Okay. So that is why we define something called a cycle life. For each of these performance parameters like storage capacity, round trip efficiency, self-discharge time, we have a certain initial value as when it's new, and we also choose a certain final value when its performance have degraded to a level that it needs to be replaced. So suppose its initial round trip efficiency was 90%. We choose 60% as the round trip efficiency, final round trip efficiency value, at which we say its life is over. Okay. Similarly, we choose a certain self-discharge time. Say the initial self-discharge time was 1 month. If it goes down to 15 days, then we say it is no longer performing the task it is supposed to do when it according to its original certification. Okay. So we choose these final degraded values, and we see how many times this energy storage material can sustain charging and discharging cycles. Okay, it is 500 times, 5,000 times or 50,000 times till its performance degrades to this predefined levels. Okay, and that many times is its cycle life. Okay, so this is again very clearly, if you see a cell phone or a laptop, its battery will become worse off over multiple use. Older laptops, you have to charge longer to get it to charge up. If you shut it down, it will discharge very quickly. Eventually you get to a situation where you have to continuously keep it charged on for it to work, because its battery cannot store much charge if at all. Okay, so that is the kind of degradation of cycle life for these batteries and energy storage technologies that we are talking about in terms of cycle life. This is very important also for automobile applications. We expect the batteries to have a certain number of cycles because we are charging and discharging every day. So how many day cycles it can sustain before the battery pack itself has to be replaced, because it can no longer sustain the automobile operation that it was designed for. Okay. So those aspects are very important. So cycle life is a very crucial parameter for energy storage systems. Okay. So today we kind of covered many of the performance parameters of energy storage. From next class onwards, we will start to discuss individual energy storage technologies and their specific uses in the sustainable energy ecosystem. Okay. So thank you for listening, and we will see you again in the next class. Thank you.